terrorista.
Hello everyone, welcome to the first video lesson for calculus and vectors. Today we're starting Unit 2, which will be a unit on the application of vectors. And we're going to start by looking at an application of the dot product, and that's a topic called scalar and vector projections. So to get started, what I'd like you to do is imagine two vectors that are sitting tail to tail. We'll call this vector A, and we'll call this horizontal vector vector B, and they of course meet at some angle theta. And we can imagine if we had a light up here shining down, straight down, this light would cause vector A to make a shadow on vector B, and if that light's directly above vector A, the shadow would make a 90-degree angle with vector B. And what we've done is project vector A straight down onto vector B, and we've created, in essence, a new vector. So again, if I have vector A and I have vector B, and I'm projecting vector A onto vector B, let's call that the origin O, where the projection of A meets vector B, we'll call that point N. So then the scalar projection of vector A onto vector B is then the vector that goes from the origin to point N. So we'll call that vector ON. Using right angle trigonometry, vector ON would be equal to the magnitude of vector A times the cosine of angle theta, or the hypotenuse times the cosine of angle theta, would be equal to the adjacent side. Let's just look at a little proof of that. And we'll look at this two ways. Using right angle trigonometry, we know the cosine of angle theta is equal to the adjacent side divided by the hypotenuse. Here the adjacent side would be the magnitude of vector ON, and the hypotenuse would be the magnitude of vector A. So cosine of angle theta is equal to magnitude of ON divided by the magnitude of vector A. If we look at this a different way, based on dot product, we know that A dotted with vector B is equal to the magnitude of vector A times the magnitude of vector B times the cosine of angle theta. If I manipulate this and isolate the cosine of angle theta, I have A dot B over the magnitude of A times the magnitude of B, and that equals cos theta. We know, based on the work we did in number 1, that the cosine of theta is equal to ON divided by A. If I cross multiply, bring that magnitude of A up, I can then cancel that magnitude of A top and on bottom. So the magnitude of ON is going to be equal to A dotted with B divided by the magnitude of vector B. So I can summarize this. If B, my vector B, is not 0, the scalar projection of A onto B is given by the formula A dot B divided by the magnitude of B. So the scalar projection of vector A onto vector B is given by A dot B divided by the magnitude of B. Going a step further, if I want to project vector A onto vector B and I want to know what that vector would be, the vector projection of A onto B is given by the formula for the scalar projection, A dotted with B, divided by the magnitude of B, times the unit vector for vector B. So here I have the unit vector. And here I have the scalar projection. So let's look at an example of how we can apply this. If I have two vectors, vector A and vector B, and they're algebraic vectors, I can find the scalar projections of A onto B, and I can find the vector projections of A onto B using that previous formula. So we'll start with the scalar projection, which is the formula A dotted with B divided by the magnitude of B, and that's equal to the vector 2, negative 3, and 4 dotted with the vector 3, negative 1, and 2 divided by the magnitude of vector B, which would be 3 squared plus negative 1 squared plus 2 squared. So performing the dot product, I multiply my x coordinates together, I multiply my y coordinates together, and I multiply my z coordinates together, and I add them all up. So I get 6 plus 3 plus 8 divided by 3 squared plus negative 1 squared plus 2 squared. So that becomes the square root of 14. I need to simplify and rationalize this answer. So in the numerator, I end up with 17 divided by the root of 14, and to rationalize, I'm going to multiply on top and bottom by root 14 over root 14. So my scalar projection ends up being 17 root 14 all over 14. Once I've found the scalar projection, I can use that information to find the vector projection. The vector projection would be the scalar projection, so 17 root 14 divided by 14 times the unit vector for vector B, which is my vector B divided by the magnitude of B. When we found the scalar projection, we found that the magnitude of B is equal to the root of 14. So we can say that this becomes 17 root 14 all over 14 times vector b, which is 3, negative 1, and 2, divided by the root of 14. Some terms cancel out. So I get 17 over 14 times 3, negative 1, and 2. Let's bring that scalar into the vector. So we'll multiply the terms of the vector by the scalar. And I get 51 over 14, negative 17 over 14, and 34 over 14. And just to finish off our answer, to reduce this, our vector would be 51 over 14, negative 17 over 14, and a z component of 17 over 7. So that's the definition of what the scalar and vector projection is, as well as an example on how we can apply the scalar and vector projections. What we've created is that vector that's pointing in the same direction as vector b, but it has that component of a projected onto it. Tomorrow in class, we're going to look at finding angles between a vector and each of the three axes. Thanks for watching.